So, continuing the series on quantum field theory, we will have to quickly review the what we know about classical field theory. So, to build a relativistic quantum field theory, we start with an effective model from a classical field theory and make an educated guess to quantize the classical field theory, right? So that's our guess. Now, the desired relativistic quantum field theory has nothing to do a priori with a classical field theory. After quantization, that is our educated guess, we take the limits of low energy, large scale, and decoherence and check that if we get back the classical field theory that we had already started with. So demonstrating whether the chosen quantization was correct or wrong enough to some level of approximation. So to start with, we will start with talking about fields, right? Now, a field is a quantity, for example, density, spin, or charge, that is defined at every point on a manifold M. Now, note over here that a rigorous definition of a field requires the introduction of vector bundles, of which I will not go so far in this video at least. We will talk about vectors in depth, in fact, in the series on general relativity, right? Okay, so we work on the Minkowski spacetime manifold, which is M is equal to M13, right? And that is simply your field R1 cross R3, right? With the field often taken to be 2 times differentiable, right? So such that the field phi c squared m rho, right? So it's 2 time differentiable, and it is defined as a function from the manifold to some target space, say rho, right? So mathematically that is written as this thing, right? So it's defined as a function from the manifold to some target space rho. So it's a map, right? It's a map to a target space rho. Now, some target spaces rho, their associated field type and example applications and models include first one, rho is equal to R, right? And that's a scalar field, and some of the examples would be a charge or magnetization, density, or the Higgs field. And the other one would be rho is equal to Rn, which is a vector field, and the examples would include the electromagnetic field, which is actually a gauge field, or a pions field, right? Okay, so a vector field, that is rho is equal to Rn, right, over the Minkowski space, that is M11, it looks a bit like, or let me just use this color, right? So it's yeah, let's see if I can draw this, right? So this over here, this space is the manifold M11, which is the Minkowski's space, and the points over here, these points, from here you have a vector perpendicular to this manifold, and this is of course the vector that belongs to Rn, right? Okay, so that was for some drawing. Now if you look at this, if you consider this, you can talk about two things, where first one is rho is equal to s squared, which is a vector field on the surface of a sphere, right? So it's a vector field on surface of sphere, right, of a sphere. And the other one, or actually let me give you some example of this. Quantum magnets, right? You could consider quantum magnets or the sigma model, right? Now another one is when you have rho as s1 cross s1, right? And this is a vector field. It's a vector field on torus, right? So that's a shape. And the examples for this is, if you have watched my lecture on the topological field theories, right, there I talked about Chern-Simons theory. So this thing over here, if you can remember, it is a Chern-Simons theory, right? And another example would be Lie groups, right? Okay, so actually note that when our target space is the n-dimensional vector field, that is this thing, right, the vector field is described as a list, that is n scalar fields, right? So the vector field is described with this set. So that's phi a of x and n, right, raised to power n, with a is equal to 1, right? And x over here is your coordinate 4 vector, right? Okay, so now that we know some things about a field, let's talk about the dynamics of a field, specifically dynamics of a classical field, right? So let me give it a heading quickly: dynamics of a classical field. Now we are going to spend some time talking about this thing, dynamics of a classical field, right? So we are going to restrict this discussion to a classical dynamics that is generated by Lagrangians. And the Lagrangians, they are obtained via the variational principle that is applied to the action functional, right? Where the system of scalar fields, that is this thing over here, right, and this a, this labels the particle type. So for example, a charge, right? Now the action functional contains a function of the Lagrangian density, right? And so that is written as this function, right? So it contains this scalar field and the 4 derivative of this field, right? Okay, so again, let me just point this out. This is again a review of classical field theory, and it's not an in-depth lecture on classical field theory, right? This is just some things that we need to remember to move on to quantum field theory, right? Some of the important points. Right, now the Lagrangian density is actually a function of higher order derivatives of the fields phi a, right? However, we make the assumption and approximation of first order derivatives. And we do that based on an observation, that is the action as a function of some omega is equal to the integral over this omega space d4x Lagrangian phi a and the this for gradient of your field. Over here, this d4x, right, that is your simply dx 0 times dx1 times dx2 times dx3, right? Okay, and this omega over here, that is a subset on this thing, looks like a C. It's a subset of M13, right, as a measurable set, and it is a region in 3+1 space-time, right? So it's a 3+1 dimensional space-time. Now typically we consider the space-time region as the entire Minkowski space. So we could then say that this omega is our M13, right? So the entire Minkowski space. Yeah. Now to extract the equations of motion, we suppose that the action S is stationary under infinitesimal variations of component scalar fields, right? So what that means is, say this thing phi a of x is some phi a of x plus some infinitesimal variation. So you could write that as delta phi a of x, right? Now this thing has to vanish on space-time region boundary, right? Such that this thing, that delta phi a of x is equal to 0 on d omega, right? Now varying the action functional, what we get is something that we call N-Euler Lagrange equations of motion. So let's go ahead and do this thing mathematically. Let's derive our N-Euler Lagrange equations of motion, right? So to do that, again, we have to suppose that the action is stationary, right? And so we are going to start with delta S of omega is equal to integral carried out over this omega d4x of partial L, which is the L is the Lagrangian density, right, over partial phi a times delta phi a plus partial L over partial times partial mu phi a, right, times delta partial mu phi a, right? So this is from calculus of variations. So I wrote this by taking the derivative of this function, right, this Lagrangian function, right? Okay, so that is just for you not to get confused. Now we said that our action has to be stationary, so what that implies is then this delta S of omega vanishes, right? So that has to be 0, and this thing is then simply your integral of phi d4x of partial L over partial phi a times delta phi a minus partial over partial x mu of partial L over partial times partial mu phi a, right, this thing multiplied by delta phi a, and you add integral of d4x over omega, right, of partial over partial x mu partial L over partial times partial mu phi a times delta phi a, right? Okay, now this last thing, right, this one is simply your surface term, right? And so this thing is partial mu m, which is the manifold mu, right? Now with this, then what you have is this above expression, right, this one, it becomes 0 is equal to integral over omega d4x of partial L over partial phi a delta phi a, right, minus partial over partial x mu times partial L over partial times partial mu phi a times delta phi a. Now if you, of course this is a review on classical field theory, you must know what we are getting at from here, right? So plus partial mu m mu, right? So this thing. Okay, so again this term, this one is known as the surface term, and it has to vanish on the boundary, right? And that is simply because we had already demanded that delta phi of a has to be 0 on the boundary, such that partial mu and mu vanishes on d omega, right? So now since action is stationary with respect to all variations of the fields, and that is delta phi a, and admissible spacetime regions omega, right? So the integrand of remaining terms must also vanishes, that is for all a, that could be 1 2 3 4 and well up to n, right? And therefore we obtain our Euler Lagrange equation, that would be this thing, right? That is the integrand, right? And it is minus partial L, let me quickly go back up there, so it's minus partial L over partial phi a plus partial over partial x mu times partial L over partial times partial mu phi a is equal to 0. Now this equation is known as your Euler Lagrange equation of motion. So with the equation of motion in hand, right, they can be encoded in the Lagrangian density and then recovered via the Euler Lagrange equations of motion. Now what does it do for us, right? That's the question. So this actually allows us to discover equations of motion with certain properties. Now one of them being symmetric under the Poincare transformations. by designing the Lagrangian densities, which are scalar under these symmetry transformations. So what we do is we apply the Euler-Lagrange recipe and get the equations of motion, which are then guaranteed to be symmetric under the chosen transformations, right? And so this benefit of the action principle is what actually makes it easy for us to design equations of motion with certain symmetries, right? So from here now, let's actually go ahead and consider an example, right? So for our example, we will consider, or we'll talk about the Klein-Gordon field, right? The Klein-Gordon field. Okay, so yeah, for this, the Lagrangian density is L is equal to 1/2 phi dot squared minus 1/2 phi squared minus 1/2 m squared phi squared, right? So that's the Lagrangian density for the Klein-Gordon field. Now you could also write this down as simply 1/2 times partial mu phi squared, right? So we're compacting it down a bit, minus half m square phi squared, right? Okay, so we have included space and time parts together in this thing, right? So over here, simply phi dot, right? It is this time derivative, time component of the derivative of phi. It's the time derivative of the field, and this thing gradient of phi j, this thing is equal to partial j times phi for j is equal to 1 to 3, right? So that is the spatial components, the xyz spatial components of the field derivatives, right? So now we will apply the Euler-Lagrange equations of motion to this Lagrangian density, right? And we will obtain the dynamics of the Klein-Gordon field, right? So if you recall from above itself, this equation was partial L over partial phi a plus partial over partial x mu of partial Lagrangian over partial times partial mu phi a, right? And this vanishes, right? So it's equal to 0. Now all we have to do from here is take these derivatives for this Lagrangian density, right? So let's see, this one is minus this minus sign, right? And then if you look at this Lagrangian, we'll have minus m square phi squared, right? So minus minus into minus m squared phi squared, right? So this minus has to come down over here, and then the derivative is this negative sign is also over here, right? Okay, so of course I don't have to go in that much depth. You can take derivatives, I hope. So yeah, and we'll have over here, we would have, look at the Lagrangian, yeah, we would have partial over partial x mu, right, of partial mu phi, right? And this thing is equal to 0. Now you could write this thing down as partial mu, right? So the contraction of these two of phi plus m squared phi, which is equal to 0, Now, this thing can be written in terms of the D'Alembert operator. So that's this D'Alembert of phi plus m squared phi, right? And this thing is equal to 0. Now, this equation, we have actually even derived this equation in very earlier videos of mine, or even in the videos on particle physics, right? In the particle physics playlist, we have derived this equation, and it is known as your Klein-Gordon equation. And so what it does is it tells you the dynamics of the Klein-Gordon field, right? Okay, so now we can finally move on to what is known as the Hamiltonian formalism, right? Hamiltonian formalism. Okay, so actually a much better way to build or guess a quantum theory with correct classical limit, and that is determined by Lagrangian density, is the Hamiltonian formalism, right? So it's this thing, right? So yeah, over here what we do is, in the Hamiltonian formalism, what we do is we calculate conjugate variables and impose canonical, or you could say algebraic, commutation relations. So suppose that this phi a of x is a component field's canonical position. Then we define the conjugate momenta, or the conjugate momentum density for each field to be as, let me write this down, conjugate momentum density. It is defined as this pi, it's just a variable, right, of x is equal to partial L over partial phi dot a, right? So this is your conjugate momentum density, and therefore that's why I have used the symbol pi, right, instead of p, because it's your momentum density. Okay, so in order to computationally study a field, what we do is we discretize space into a regular lattice, right, with some spacing. We'll call that epsilon, right? So that is the spacing between each lattice site. Now, since representing a continuous object on a computer would obviously require infinite amount of data, so that's why we have to, when we are studying this computationally, we have to discretize our space. Now, discretization yields generalized coordinates, and they're defined by the field itself, of the form that is q j of t, right? There's a is equal to phi a of t xj, where this j belongs to this integer fields, right? So it's integers, right? Now let me actually first visually show you what I'm talking about. That is, consider that this line is some x direction, right? And you have a field along this line, right? And we'll call this phi a of x. So this is your field. And now this is a continuous field, right? Of course. Now what we do is we discretize this as we take points for this, right? So what we are going to do is say we need to take points that form exactly this field. I don't know if this looks like the line that I have drawn if you join all these points, but that's what it's supposed to do. And so for each point, we have some xj. For the next point, of course, we will have some xj plus 1, right? And so on, of course. And so if you consider these lines, right, these positions for these points, this spacing is what we call epsilon, right? Now again, this was over some x. So to discretize the action functional and apply the variational principle, we have to replace our partial derivatives, which were again partial mu phi a dx, right? We have to replace these. Why, you ask? Well, this partial mu, it is a continuous operation, right? But we need to discretize our action functional, right? So we do that by simply applying Taylor's theorem to approximate a spatial component of the field as some finite difference. Now over here, this epsilon, this thing, it has to be made as small as possible, so such that the error approximation is minimized, right? Now what we can do is we can replace this as, if we apply the Taylor's theorem, we get this partial x phi a t x, right? This thing, it is approximately equal to phi a of t x j plus some epsilon, right? That spacing that we talked about, minus phi t x j over epsilon, right? Now this thing is simply your Taylor expansion, or the Taylor's theorem applied on this derivative, right? So we have just turned our continuous derivative into an approximate a discrete derivative, you might call it, right? And which is this thing is further equal to, you could say, qj plus 1 minus qj, right, and divided by this spacing epsilon. However, what we are going to do is we will leave the temporal component to be continuous, that is the time component. So this means that this thing will remain as it is. Xj is equal to, or at least approximately equal, or let's just say it's equal to q dot j, right? Okay, so now we have to get the Lagrangian. Now to obtain the Lagrangian, we have to integrate the density over the space, such that only the time dependence is then left over. So mathematically what I'm saying is that we take this integral d3x of this Lagrangian density phi a partial mu phi a, such that we are left with this thing, Lagrangian function a j as a function of t and q dot j a as a function of t, right, which is simply your Lagrangian as a function of time, right? So if you take this integral, you are left with time dependence of the Lagrangian. Now the discrete approximation of the Lagrangian is then written as L of t is approximately equal to summation j delta x j Lagrangian density of phi a of t x j, sorry, there is no a over there, yeah, and let me make this bracket, yeah, and we have over here the derivative part, so that's partial mu phi a of t and x j. Right, so if you don't understand, what I have done is we had integral over here, right? So that's continuous. We have to discretize that, right? So that's that's why we took this summation and this thing, right? So that's how we obtained the discrete approximation of the Lagrangian, by discretizing it, of course. Now, with this, then, if you recall how we defined our momentum density, we can obtain the discrete conjugate momenta, right? And that is the P j, which is a function of time, is equal to partial L over partial q dot j a, which is equal to summation over j times of delta xj multiplied by partial L over partial q dot j, which is equal to summation j delta xj times pi a x, t and xj, right? So this thing over here is the momentum density multiplied by some delta xj. That's how we get this discrete conjugate momenta. Right, now what we can do from here is quickly look at a simple example, right? And for that we are going to consider the Lagrangian density, right? So let me just write over here example, and we're going to consider the Lagrangian density, which is 1/2 partial mu phi, which can be expanded into time and space parts as 1/2 partial time derivative of phi squared minus 1/2 partial x, the spatial part, right, phi squared. Now we have to integrate this over space d3x to obtain the Lagrangian and discretize it using the rules that we just defined over here, right? All these ones. Now, in fact, what I'm not going to do this, right? It would be a very good exercise for you to do it on your own self. You just have to follow along these rules that I told you. For to obtain the Lagrangian, you integrate it over the space d3x, and then you discretize your Lagrangian as such, right? Now once you do that, what you will get is L of t is equal to 1/2 summation j is equal to minus infinity to infinity epsilon dqj over dt squared minus this thing qj plus 1 minus qj, right, over epsilon. So this is what you will get. Now over here, this epsilon is simply your delta xj, your epsilon times this whole thing. I mean, of course, if you remove this square, right? So what I mean is this thing epsilon times dqj over dt is simply your conjugate momenta, this thing, right? And yeah, that's it. Now if over here, if you were to take a limit as to taking this epsilon going to 0, right, what would happen is, then say if I were to take this limit, what I would get is that my qj of t, this generalized position, goes to this field, right, as a function of time and position. And likewise this momenta, it goes to phi dot of dx, where phi dot is simply the time derivative of the field. Now finally we can talk about something that is called the we have talked about Lagrangian density, right? Let's talk about the Hamiltonian density. Right, so we'll quickly talk about this. So for a discrete approximation, the Hamiltonian obtained by integrating the Hamiltonian density, which is this thing, of space that is d3x, right? This thing is then h that you obtain from the Hamiltonian density can be written as summation j p j q dot j minus the Lagrangian L, right, which is if you want me to write it down, which is simply summation j delta xj of this thing pi a, which is a function of t xj txj, and times phi dot tx, right, minus the Lagrangian density, right? So this thing I have written in terms of the density. So now in the limit as to the limit epsilon goes to 0, the Hamiltonian density then becomes this thing, that is this htx. This is the Hamiltonian density, which is this momentum density times phi dot a tx, right, minus this Lagrangian density, which is function of phi a tx, and the gradient or the derivative, which is partial mu phi a tx, right? Okay, so now again you could do this as an exercise. You could consider the same Klein-Gordon field that we talked about, and you could find out the Hamiltonian density for that field using this expression that I have just written over here. And what you would get is, or at least if you drop the field index and space-time dependencies from the expression, you would receive 1 over 2 pi squared plus 1 over 2 squared plus 1 over 2 m squared phi squared, right? Okay, so with this we have covered almost everything, or let me just circle this. We have covered almost everything that we need for quantum field theory, that we need from classical field theory, right? So in the next lecture on quantum field theory, we are going to talk about the symmetries in classical field theory, which will also lead us to talk about the Noether's theorem, right? of symmetries. Now, after we are done with that, that is when we can proceed towards the quantization of the field, right? And then slowly we will dive into the quantum field theory, right? So that's it.